In this episode, we step into natural language processing, which is the part of data and AI work that deals with text, and we focus on the foundational ideas that make text usable for modeling. Beginners often think text is just another data type, but text is different because it is messy, ambiguous, and full of context that humans handle effortlessly while computers need explicit representation. In cloud security and cybersecurity environments, text shows up everywhere, from incident tickets and analyst notes to alert descriptions, configuration snippets, and user-provided fields. If you can handle text responsibly, you can unlock valuable signals that are otherwise trapped in free-form language. But if you handle it carelessly, you can create privacy risks and misleading patterns. The essential move in natural language processing is turning text into numbers in a way that keeps useful meaning while being stable and explainable. We will focus on tokenization, embeddings, term frequency inverse document frequency, TF-IDF, and topic models, because these ideas form the backbone of many practical text workflows. The goal is to build intuition so you understand what each technique is doing and what trade-offs it introduces. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first step in most text workflows is tokenization, which is the process of breaking text into smaller units that a model can work with. A token can be a word, a part of a word, a character, or even a punctuation segment, depending on the strategy. Tokenization matters because it defines the basic pieces of meaning your representation can express, and different tokenization choices can change what the model notices. In security text, tokenization is tricky because many meaningful strings are not normal words, such as file paths, domain names, command fragments, and unique identifiers. If you tokenize too aggressively, you can split meaningful items into useless pieces, and if you tokenize too conservatively, you can treat many unique strings as unrelated, losing generalization. Beginners often assume tokenization is just splitting on spaces, but that approach fails on punctuation-heavy data, and security text is often punctuation-heavy. A professional mindset begins by asking what units of text represent meaningful categories for the task, such as whether you need to capture error codes, product names, or action verbs. Tokenization also interacts with privacy because tokens can include names, emails, or sensitive identifiers, so you must decide what should be preserved, masked, or excluded. Thoughtful tokenization is the foundation of safe and useful text modeling. Once you have tokens, you need to convert them into a numeric form, and one of the simplest representations is a bag-of-words approach, where you count how often tokens appear in each document. A document can be an email, a ticket, an alert description, or any unit of text you choose, and the choice of document boundary matters because it defines what context you are capturing. Bag of words ignores token order, which is a limitation, but it can still work well for many classification tasks where presence of certain terms matters more than sentence structure. In security operations, a ticket that contains specific malware family names or specific error messages might be classifiable even without order, because key terms carry strong signals. The problem is that raw counts can be dominated by common words like the or and, which are not informative, and they can also be dominated by frequent terms that appear in many documents. This is where weighting schemes become important, because you want the representation to emphasize tokens that distinguish one document from another. Beginners sometimes assume more words automatically means more information, but common words add noise, and repeated words can inflate counts without adding meaning. The bag of words idea is useful because it clarifies that text modeling begins by creating measurable features from tokens. Term frequency inverse document frequency, TF-IDF, is a weighting scheme that addresses the problem of common words by downweighting tokens that appear in many documents. Term frequency reflects how often a token appears in a specific document, while inverse document frequency reflects how rare the token is across the entire corpus. The combined weight is higher for tokens that are frequent in a specific document but rare across documents, which often corresponds to terms that are more informative. This is why TF TF-IDF is a strong baseline for text classification and clustering, especially when you need a method that is interpretable and efficient. In cloud security contexts, TF-IDF can highlight meaningful tokens like specific error codes, product names, or unusual process strings that distinguish one incident description from another. The beginner misunderstanding is to treat TF-IDF as a magical model rather than as a feature representation, because it does not directly classify. It just transforms text into numeric vectors that models can use. Another misunderstanding is assuming TF-IDF captures meaning, when it primarily captures token importance under frequency patterns, not semantics. Still, it is valuable because it often works well and because you can inspect which tokens have high weights, supporting explainability. In environments where stakeholders need to understand why text influenced a decision, that interpretability can be a major advantage. TF-IDF also has limitations that you need to recognize to use it responsibly. Because it is based on token counts, it cannot naturally handle synonyms, meaning two different words with the same meaning will be treated as unrelated features. It also cannot capture context shifts, like the difference between benign and malicious uses of the same term, because it does not model order or relationships between tokens. In security text, this can matter because terms like admin, scan, or test can appear in both benign and suspicious contexts, and the surrounding words often determine meaning. Another limitation is that TF-IDF can be sensitive to how you define documents and how you preprocess text, such as whether you lowercase, remove stop words, or normalize punctuation. It can also be sensitive to vocabulary size, because rare tokens can receive high weights even if they represent typos or unique identifiers that do not generalize. Beginners often see high-weight tokens and assume they are important in a meaningful way, but sometimes they are artifacts of formatting or random, unique strings. A thoughtful approach includes cleaning and normalization that reduces meaningless uniqueness while preserving security-relevant tokens. Using TF-IDF effectively means treating it as a strong baseline and combining it with careful pre-processing and evaluation. Embeddings are a different kind of text representation that aims to capture semantic relationships, not just frequency patterns. Instead of representing text as a sparse vector where each dimension corresponds to a token in the vocabulary, embeddings represent tokens or larger text units as dense numeric vectors where similar meanings tend to be close in the vector space. The core intuition is that the model learns relationships from large corpora, so words used in similar contexts end up with similar vectors, which allows generalization across synonyms and related terms. In security contexts, embeddings can help you capture that phishing and credential theft are related even if they are different words, or that certain error messages cluster together because they describe similar failure modes. Embeddings can also represent larger units like sentences or documents, which can be useful for clustering tickets, searching incident reports, or classifying alert descriptions. The beginner trap is to treat embeddings as perfect meaning encoders, when they are learned representations that can reflect biases in the training data and can blur domain-specific meanings. Security terms can have specialized usage, and general embeddings may not capture those nuances well. Still, embeddings are powerful because they allow models to work with meaning similarity rather than strict token identity. Understanding how embeddings work at a high level helps you avoid overclaiming and use them more safely. Embeddings are typically learned by training a model to predict words from context or context from words, or by learning representations that are useful for downstream tasks. The training process encourages vectors to reflect co-occurrence patterns in large text corpora, which is why similar words end up near each other. For beginners, it is enough to understand that embeddings are learned from data, not invented by rules, and that the geometry of the embedding space encodes relationships learned from usage patterns. This means embeddings can capture helpful associations, but they can also capture unwanted associations, including stereotypes or domain mismatches. In cloud security work, embeddings may accidentally associate certain terms with risk based on biased historical incident reports, which can influence models in subtle ways. Another practical issue is that embeddings can make explainability harder because the features are not human-readable tokens, but numeric dimensions. You can still explain using nearest neighbors and example-based reasoning, but it is different from pointing to high-weight tokens in TF-IDF. Using embeddings responsibly means combining their semantic power with careful evaluation and, when needed, additional explainability strategies. Tokenization remains important even when you use embeddings, because embeddings still depend on how you break text into units. Many modern embedding approaches use subword tokenization, which splits rare or complex words into smaller pieces that can be combined, helping handle misspellings and rare terms. This is particularly relevant in security text, where you encounter unusual strings, product versions, and mixed alphanumeric identifiers. Subword approaches can help represent new terms by composing them from known pieces, improving generalization. The risk is that subword tokenization can also split meaningful identifiers in ways that leak information or create spurious similarity. For example, two unrelated identifiers might share a prefix and therefore end up closer in representation than they should, which could distort clustering. Beginners sometimes forget that even advanced representations rely on foundational preprocessing choices, and those choices can dominate outcomes. A safe approach is to treat tokenization and normalization as part of the representation design rather than as a default. In security contexts, you also consider masking patterns like emails or long IDs, so the model focuses on structure and meaning rather than on personal or unique details. Tokenization choices are therefore both modeling choices and governance choices. Topic models are another essential concept because they provide a way to discover themes in collections of documents without labels, which can be useful for organizing large volumes of text. A topic model tries to represent each document as a mixture of topics, where each topic is a distribution over words, meaning certain words are more likely under that topic. Conceptually, a topic is not a human-defined category, but a statistical pattern of co-occurring tokens. This can help in security operations by revealing common themes in tickets, such as authentication issues, malware-related reports, policy violations, or access requests, even when those categories were not labeled consistently. Beginners sometimes interpret topic models as finding the true underlying topics of the world, but topic models find patterns that depend on preprocessing choices, vocabulary, and how you define a document. Topics can also be hard to interpret because a topic might combine words that co-occur for multiple reasons, including shared workflow language rather than shared incident type. Still, topic models can be powerful for triage, summarization, and discovery, especially when used as exploratory tools rather than as final answers. A thoughtful approach treats topics as lenses that help you navigate text corpora. Topic model evaluation is another place where beginners can overclaim, because it is tempting to treat topics as inherently meaningful once they look coherent to a human reader. In practice, topics can look coherent while still being driven by artifacts, such as ticket templates, common signatures, or repeated phrases used by certain teams. This is why preprocessing and standardization matter, such as removing boilerplate text that appears in every ticket, because otherwise the model will create topics about the boilerplate rather than about the underlying issues. Topic models also vary in how many topics you choose, and choosing too many can produce fragmented, hard-to-use topics, while choosing too few can merge distinct themes. In cloud security settings, topic models can help detect emerging issues, such as a sudden cluster of reports about a new authentication failure. But you must confirm whether the pattern reflects a real operational change or a reporting change. The value is often in the trend, such as which topics are increasing, rather than in the exact definition of a topic. Beginners should learn to treat topic models as hypothesis generators that require validation and interpretation. This keeps them useful without turning them into false authority. An important theme across tokenization, TF-IDF, embeddings, and topic models is privacy, because text can contain sensitive information that is not obvious at first glance. Ticket notes can include names, emails, customer details, or internal system identifiers, and even if you do not intend to model those, they can become features. In security environments, text might also include fragments of configurations or logs that expose internal structure. A professional approach includes scanning for sensitive patterns, masking or removing sensitive fields when they are not needed, and enforcing access control on text datasets because they are often more sensitive than structured tables. Beginners sometimes think privacy is handled by removing a name field, but in text the sensitive content is embedded throughout, and identifiers can appear in many forms. This is why preprocessing is not only about modeling performance, but also about governance, ensuring the representation does not accidentally encode personal details. It also affects explainability, because if you surface influential tokens or nearest neighbors, you could reveal sensitive details and explanations. Responsible text processing, therefore, includes thinking about what will be shown to humans and what must be kept restricted. When you treat privacy as part of representation design, you reduce risk while still extracting useful signal. Bringing everything together, natural language processing essentials are about turning text into stable numeric representations that models can use while respecting the messy nature of language and the sensitivity of text data. Tokenization defines the units you will measure, and in security text, that choice must respect punctuation-heavy tokens and domain-specific strings. TF-IDF provides a strong, interpretable baseline that emphasizes distinguishing tokens, but it does not capture semantics or context beyond frequency patterns. Embeddings provide dense representations that capture semantic similarity, enabling generalization across related terms, but they can be harder to explain and can reflect biases or domain mismatch. Topic models provide unsupervised discovery of themes, which can help organize and monitor text corpora, but topics are statistical patterns that require careful interpretation and validation. Across all methods, preprocessing and governance decisions, especially about masking sensitive content, influence both usefulness and safety. When you can explain these techniques in terms of what they represent and what they miss, you can choose text approaches that match your task and avoid overclaiming what a representation can prove. That disciplined understanding is exactly what helps you succeed on the CompTIA Data AI certification and build text-driven security analytics that are both valuable and responsible.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.